Hi, I'm Darren and welcome to Level Up EE Lab. I'm finally going to get started on the Sencore FE149 meter that I picked up at last year's Hamvention. And in fact, I was so excited to get started working on it that I forgot to film the intro after I already started disassembling it. So let's see what I found so far. This is my Sencore FE149 analog multimeter. Now, Sencore is not a name you hear much of today. They still are around. They seem to make mostly specialty commercial video gear nowadays, not test instruments like this anymore. This particular model, the FE149, is about 60 years old. I date it to the mid to late 1960s based on some information I found online, including a manual that had a schematic in it that was dated 1969. Now, they do have catalogs online, or folks have scanned their catalogs rather, and it appears in the 1971 catalog, but not in the 1974 catalog. So that kind of puts a rough bookend on when it went out of production. And I happen to have another piece of Sencore gear, my Mighty Mite TC162 tube tester is from the same era, and shares some common styling features. So got a couple Sencore pieces of equipment in my lab now. This particular one I picked up at Dayton Hamvention last year, and you can see the earlier video for it and the several other items that I picked up at bargain prices. I only paid $10 for this. Of course, I have no idea if it works, but I was immediately attracted to this nice, huge meter on the front of it. It's almost 7 inches across, and compare it to this guy, my Heathkit analog AC meter from roughly the same era. You can see how much bigger that display is than that one. This is about 4 inches across, and this is very common size for Heathkit instruments and other test equipment from the same rough era. So I just could not pass up this guy with his huge scale. Now, it also has a mirror on it to help eliminate or reduce some of the parallax, and the graphics on it are superb. And I'll try to use my other camera to get a zoom in shot. It's just very difficult to try to photograph or video something like a meter that's reflective straight on, but I'll do the best I can here to show this. But in particular, the red text is still very bold. That is the first thing to go, I've noticed on a lot of these old analog meters, because if there's any sunlight in the room, the red ink that they use just doesn't hold up and it fades pretty badly. But this is nice and bright. So this probably didn't spend much time out on a shelf where there was sunlight. What else about it? It features 2 big rows of push buttons here. The red row of buttons here, these are your functions. Of course, you got voltage and current, both DC and AC, that you can measure. And then the row below it is the various ranges. So you select what mode here with the red buttons, and the row of black buttons, you select which range you're going to measure. And there's a lot of text on here. So this front panel is very busy, but at least it tells you exactly what buttons to push for what function and what range you want. And down at the very bottom, there's an on-off switch. The test leads are permanently attached to it. They're not replaceable or not swappable. You have to use the ones that it came with. And then there's a small jack down here where you can plug in an additional test lead to enable to measure up to 5 amps of current. Styling wise, let's look at that a little more closely. The case, it looks like it's painted, but it's not. I'll try to get the lighting on here so you can see maybe up at the top up here, this texture. This is vinyl clad steel. Ooh, another dead giveaway that this thing is from the 60s or 70s. This technique, this manufacturing technique was used a lot on AV gear, on test equipment. It's similar to the vinyl top on an old car. Not quite exactly the same material, but very similar. They just coat the steel with vinyl. And then around back, of course, there's a fuse, since it can run off of AC power. And right away, I run into my first little difficulty. That is another weird or kind of unique 3-prong jack, and I don't have a cord that fits that. So one of the things on the short list will be seeing if I can replace that jack with a modern jack and use a modern replaceable cord. Now down here at the bottom, I showed in my earlier quick video on this, there is a panel to remove, and inside this panel is a space for two batteries. One is the 1.5 volt D cell, in this case, that you'd use when you're checking resistors, when you're using the ohms mode. And the other one is actually a rechargeable 9.6 volt battery. This guy, believe it or not, was intended to be portable. Take this thing out into the field compared to your modern small DMMs when you're trying to make measurements in the field. It would run off of its own internal 9.6 volt battery, or you can plug it in, like I said earlier, to AC. Unfortunately, that battery is missing, but even if it was in there, I don't think it would be good after 60 some years. So up next, of course, is to start disassembly and see what's going on inside. Like I said, I don't know if this works or not, but I'm going to find out real quick if there's anything alarming in here. All right, I've removed the case from the chassis, and it was actually very easy to do that. There's just 4 screws that hold it in place, and it slides right off the front. No big deal. In initial inspection, this actually looks to be in really good condition. There's no obvious signs of aging, nothing looking burnt or corroded, the only exception being the contact point right here for the 1.5 volt battery. Somebody definitely left an alkaline battery in there a little too long and it started to leak, but that's easily fixed. The 9.6 volt rechargeable battery, it's long gone. Somebody cut it out. No big deal. I wasn't planning on using it anyway. As far as the overall construction goes, it's really solid. There's a copper-plated steel chassis, or maybe even solid copper chassis here, and then 2 circuit boards, a small one and a large one. The small one contains mostly just the range control switches, and the large one contains the function switches along with the rest of the circuit. Let me try to turn this around and take a look at this top circuit board. And getting the lighting on here and the focus on here is a little tricky because of this thing here. The camera just wants to focus on that. But if I zoom in, there we go. That might actually work. Try to get some lighting on it. So what's going on here? There's just a few electrolytics, one for the power supply, of course. And there's about 9 or so of these turquoise colored caps. I do have a owner's manual with a schematic and a parts list in it that I found online. Unfortunately, it doesn't match exactly the vintage of this unit, but where it does match, these are identified as Mylar caps, which is a trademark for polyester. And unfortunately, polyesters are prone for electrical leakage over time, so these are a concern. They might be leaky. There are quite a few polystyrene caps scattered throughout both boards as well, especially for smaller values like pico, the tens or hundreds of picofarads. And those generally don't go bad with time, for what I understand doing my online research. But if they do go bad, they are unobtainium. Nobody makes polystyrene caps anymore. So hopefully I don't have to deal with that. And also, speaking of rare parts, you can see them right here, and right here. In fact, let me get a pencil, poke a little better right there, there, and there. Those are 3 of the 2N5163 FETs, which were very early generation field effect transistors. And those also are pretty hard, if not close to impossible, to find anymore. So hopefully those are also good. And in fact, looking at that same manual, I'm pretty sure that the ones that make up the differential amp are matched pairs. So hopefully those are still good. What can help me out here, though, is I can first test if the power supply is working. I can do that quite easily. On the front of the unit, there's a special mode for testing that rechargeable battery and seeing, what its charge is. And when you push that button in, what happens is the power supply, the AC to DC power supply, is completely disconnected from the rest of the circuit. So I'll be able to put this on the dim bulb tester and power it up and make sure I've got good DC voltage. If I do, then I can proceed to test out the rest of the unit and make sure that at least it's basically working before I commit to spending any more time or money on it. Okay, I'm ready to test out the power supply, and of course I'm using my dim bulb tester right here with its AC output connected through some clip leads to the AC power input jack on the meter. Now, it is a bit dodgy, but in this case, I don't need to put my hands on the unit to make these measurements. I don't need to move it around at all, so it's fine just to temporarily hook up AC power this way. The bulb, of course, is going to limit the current in case there's something really wrong in the meter, and you might think that the fuse would help protect in case of something drastic, but in the actual way that Sencore constructed this meter, that fuse is not on the primary side. It's not on the secondary side of the power supply. It's actually in series with the black test lead. And in the manual, they say the fuse is there to protect the meter circuit if you're measuring, for example, current and you accidentally put too much current through the meter. The fuse will protect the internal circuitry. Or if you're measuring ohms and apply high voltage to the test leads, it'll help protect the meter. So they also explain that the output impedance of the power supply is high enough that you can short it and it won't cause a problem. I'm not going to test that. I'll just take their word for it that it's really capable of withstanding that. So I've got my scope probe connected up here to the output, and more specifically, it's connected across diode CR4, which is the Zener shunt regulator. Now, with any test, it's important to define your acceptance criteria before you start. What do you expect to happen? And can you quantify your expectations? So in this case, it's pretty simple. What I expect to see as I slowly raise the AC input voltage is a steadily increasing DC output from the power supply. I've got the scope set up, and it's not that clear on screen, but I've got it set up at 2 volts per division, and I purposely moved the trace near the bottom of the screen so we can see it better. So I expect that yellow line to start rising as I raise the AC input voltage, but as it approaches the breakdown voltage of that Zener diode, which is a 12 volt Zener, that voltage should stabilize at around 12 volts and not go any higher. And of course, I expect there to be no ripple. It's there as a shunt regulator to provide clean DC voltage to the circuit, and that's what I expect to see. So pretty simple test. Should only take a minute to check it out. So here we go.
This item contains hazardous voltage and safety precautions must be followed. If you're following along and working on your own version, you're doing so at your own risk.
Start increasing the AC, and you can see that yellow trace starting to go up right away. So I'm up about 15 volts AC. There's hardly any ripple on it, so that's also good. And I know you can't see it, but the bottom of the scope screen has the measurement function turned on, and I'm at about 7 volts DC right now with 42 volts AC input. Let's keep increasing. I'm up at 10 volts right there. And remember, I need that to plateau around 12 volts, and it is plateauing. It's at 11.6, even though my AC is still increasing. It's now plateaued. I don't see any magic smoke or anything else alarming happening over here, so I'm going to keep going until I get to about 115. And remember, the power supply is isolated from the meter circuit right now. There's no load on it. All right, there we go, 115 volts AC. That continues to be plateaued at between 11.6 and 11.8 volts. So I'd say this test is a success. So next, I'm going to break this down and then check out the rest of the meter circuit and see just how much of it still works. Okay, I arranged a more secure power cord. I temporarily soldered in and secured this cord so there's no more jumper leads holding on the AC power. And I turned the meter on and started checking out some of its functions, and unfortunately the news is not good. It's not good at all. It's not working. Let me show you what I mean here. So I've got it set right now on DC minus, and one thing right away you can see is the DC, or the zero adjust control rather, has no effect. If I put it on DC plus, the needle is pegging in a negative direction. Same problem. And put it back here on DC minus. I've got the range set to 15 volts. This is a good 9 volt battery. And I know it's good because I'll show you another measurement here in a minute that shows that it is. And so if I hook it up, and nothing's happening. Even if I reverse the polarity, nothing's happening. So that's not a good sign. I also temporarily put in a D-cell battery back here and clamped it so that the connection was good. Ohms function is not working, but what is working is the current. And if I put this on plus DC current, I'll take the same battery. And let's see, let's put the range on 15 milliamps. And I've got a 1K resistor here. And if I do this correctly and don't short things out, we should see the meter move. So put that, oh, let me get that polarity correct. Yeah, this, see what I mean? You got to be careful here, not short things out. This will be on the negative, this will be on the positive, and then this will go on the test lead. Aha, the meter's working, and it should be around 9 or so milliamps. You can see it's reading a little high, but that's okay. I'll forgive it if it's not in cal. So the meter is working, but I can't get too excited because I look in the manual and essentially the meter works even when it's off. The FE149 doesn't use any of the internal circuitry when you're measuring DC plus or DC minus current. Essentially, it's just a bunch of series resistors that control how much current goes through the meter, so you can measure current without the meter even being turned on. So there's definitely something anomalous, maybe more than one thing anomalous, and I'm going to have to spend some more time to troubleshoot the circuit and see what's going on. Where to go next? Well, one thing that I did off camera was measure the voltages on all 3 FETs. The manual gives a little bit of guidance here. It says that the source voltage in all 3 of them should be 4.7 volts. Now, it doesn't say under which conditions, so I just assumed quiescent, powered on, and no load on the meter. And what I got for TR2 and TR3 was 4.3 volts, so a little bit low. But more concerning was TR1. It was quite a bit lower at 3.12 volts. Now, right away, that makes me suspicious that there could be some electrically leaking capacitors in that circuit. It's a high impedance circuit, and it would not take much leakage current to throw it off and make it malfunction. So that's what I'm going to focus on next. And I may have to, lift one lead, unsolder one lead of a cap to get it out of circuit, and then run it through my capacitor tester and see what I can find. But to be honest, I'm not willing to put an enormous amount of effort and certainly not an enormous amount of money into this $10 meter to get it working. Hopefully, in the next episode, I will find what is wrong with this, and hopefully it will be something simple and economical to fix. As always, I hope you guys are enjoying the content here on my channel. And until next time, bye for now.